tea break. So please.
Thanks very much. And so I thank the organizers not just for bringing us here and inviting me, but also I thank Michelle for agreeing to this kind of schedule that was accommodating my difficult full schedule. When I got the invitation, I thought I'll speak about the most recent work we've done on Rydberg Physics, which is very dark with me. But then yesterday there was so much interesting control, and I talked to Shannon in particular, so I thought I'd do a few extra slides just to get the point across. And I would like to highlight first the new notebook that my student in my assistant came up with. So for those of you who have been to Berlin, maybe you recognize the Berlin City Tower, which has been put into a mathematical composition state, thanks to some shape article that I think so that's the name of the game. What is control? And I'll answer this question from a slightly mathematical perspective, because control in this room means many things to many people. And then control theory, it refers to steering a dynamical system from some initial to some final state using external knobs. And a dynamical system is any system that you can turn and that's an old and well-established theory with many applications. One of the most famous ones, the landing of the Apollo mission on the moon. And you can boil this down nowadays to a text homework problem. If you treat the spacecraft as a point particle, and then the relevant equations of motion are of course Newton's equation because they have to be found out. And your control now is to change the acceleration according to. You can sit down and use variable calculus and really divide the closed form expression. More generally, this is part of what people refer to as optimal control theory. You want to reach a certain target with a desired accuracy, typically with some minimum expenditure, minimum time or minimum energy for you to show that there's another example that maybe some of you know back to childhood days in addition to a space. We're here talking about applying this mathematical framework to quantum systems, which can be the operation of a set of qubits, conditional gates, or whatever you fancy. So why do I bring this up in this context? Well, because Rydberg atoms are just really perfect for applying this set of tools. So before we get there, just maybe one more slide of adding. So my preferred version, personal preferred version for actually carrying out quantum optimal control goes back to the mathematician Diamond Farber. It's based on directional calculus as the first year. So the first order derivatives have two baggage. It's a gradient-based optimization, which are the set of methods which converge very nicely. And I like Farber's version because he has a constructed point that allows you to take this to a very, very general framework, so you can have nonlinear equations of motion, including dissipation. You can have nonlinear controls. For example, when the electric field couples to some power square or non-convex target functionals, which is what you get when you optimize when you play with content of some dynamics in percentages of the state. So it's nice to have this flexibility. And a couple of years ago, we put out the Python implementation, including examples, workload examples, both systems, open system. And I invite you to have a look at your interest, in particular the students. And it's nice to do this advertising here in UCL, because this is one of the places where we work exactly like I had dreamed of when we put this out. Because about 2 years ago, I was contacted by Ernesto Serafini, who's here in the physics department. And a master's student from his group had started to play with this package, and that was some first result, and we just really double checked it with what I thought about it. And the master thesis in the end were the nice. So, as I said, if you're interested in solving this type of control problems and you need this type of flexibility, then go into it. And you may not always be able to respond immediately, but you will get a response if you have questions or not. in the documentation. Okay, so now let's go back to Rydberg atoms. Here's an example where we can apply this and that illustrates why Rydberg atoms are such a nice playground for this type of tools. So our goal was, and that was actually brought forward to us by the group of Christiane Koch and Sebastian Lenz to prepare these circular states. So here's the Rydberg upgrade, this is the Rydberg to scale. Where the electron is in the maximal projection quantum number either positive or negative. And first of all, why this kind of Rydberg states and not any with a low projection quantum number? Well, the main answer is because of the super long lifetime of those states. So you can use them as quantum sensors, as the parent group has shown a few years ago, and also for quantum computing, as Mark put forward, many as well, provided we can actually prepare them faster. This is what I'll get to, but just to highlight the point of the sensor once more. So here are two of such circular states for different principal quantum numbers. And the point is, now we use a non-classical superposition of those circular states and then upgrade an interferometer on the manifold marked in red. Now here, we move from a kind of classical state protocol to one where we really exploit the relative phase between these two circular states and resolution. So there's plenty of applications for these things. And typically, if you do a Rydberg excitation with lasers, you end up in something like m equals 1 or 2 or maybe 3, depending on how many photons you use. But then you want to go all the way to 50 or the manifold, whatever. And then these states are almost equally spaced. So you can use a generalization of the pipe instead of the simple protocol that you can do now. But there are limits, because if you operate it slowly, then the decoherence on the way to the circular state hurts you. And if you shorten it and make it faster, then eventually you'll go not only from the initial state to the target, but also to get stuck in some of those lower states. And this is the experimental protocol, this is the experimental data from the James group, where they got to about 80% with this type of paths that you can calculate. So for us, this was a really nice control example. Why? Because also we know we have opponents as well of those things, right? It's a Rydberg atom in an electric field, so everything is described by perfect representation theory. From energy levels, matrix elements, perfectly clean system. So here's the solution that we can up with. And you see, you can take it to the experiment, and even though the experiment is under the 5-step, and you expect the distortion of the control and unpleasant things like this to go on, it works like a charm. It's upgrading 99% and then measuring 7% fidelity, and the pulse is being like too crazy. And if you look at this pulse, then maybe you ask yourself, well, then, like really, then you just have a constant amplitude in the second half. So what's going on? How does this actually work? From the negative in the beginning, you need to create a spin coherent state from your clock state. And once you have a spin coherent state, then all that you do is locate the one corner of the gibbons. So what we actually got was answer the breaks doesn't optimally give you very complicated pulses, well it does, but once you understand what's going on, we have the signals actually, and you realize you don't need them, it's just flatten them out and see what's interesting. And after this comparison experiment in theory works so nicely, my colleagues from Paris are really ambitious and said, well now let's target something that we don't even know how to prepare this state. Let's look at the 50-50 superposition of the circular state and the low-end state. And you see that once again, it was fairly simple. You understand what's going on there. And the fidelity is essentially the same as the circular. And also the terms of the okay. So this is once more the reason why you can take the pulses and calculate them in the theory and just put them on your arbitrary generator is because the Rydberg energy is so accurately relevant. Okay, now I come to the actual subject of my talk, and I completely turn around the perspective. I don't want to control Rydberg atoms now. I want to use Rydberg atoms as a way to control molecules. And this tied in with some of the things that Rosario mentioned earlier in the morning. And in particular, I want to look at doing spectroscopy of polar molecules using what is called Förster Resonance Energy Transfer. So probably most of you in the Rydberg community know what it is. If you have a transition in the Rydberg atom that matches in transition energy to one in the molecule, the two particles may exchange this energy resonantly. So the Rydberg atom flips its state in some of the molecule. And then if you detect the Rydberg atom, you know whether the molecule is in the same category or not. So, but before I go into more detail and also acknowledge some of the work that has been already done in this field, let me give you some more motivation of cold polar molecules. Again, some of this was mentioned by Rosario, for example, quantum sensing and metrology. So this is there is a reason resurgent interest, mainly in the context of fundamental physics, so using molecules for cavity violation measurements or EDM measurements. And there are these things nicely used that summarize the ongoing interests really interesting. The other one is quantum computing. So here again, the picture that Rosario has shown, the early work by David Mill and some of the more recent work in Preston and algorithm. So there is sufficient interest that justifies to do experiments with those molecules, and maybe a little bit strange for theoreticians to think about the problem, which on first glance was mainly experimental, and how do you actually detect those features? I think it's a conceptual problem and it deserves interest on its own. And the point is that in view of such applications as sensing or computing, it's really bad that most of the existing methods are actually destructive. So what, for example, what is used by Tanquini and also many others, like in that elaborate setups, is absorption imaging of atoms. So what they do is they redissociate the molecules and then they image the atoms because the atoms molecules. But it's dissociate and then image the dissociation that it's a molecule. The other more traditional approach is supplementary, rather than some total ionization that was used, for example, in the book of the but also from many others, where you ionize the molecules and then you would have a fragmentation of the ions or have something to do with this. And in both cases, so here you dissociate the molecules, here you ionize them, the molecules are gone. And if you want to use them as sample for computing, it's too good that it's not so good. So there have been theory proposals how to do the detection non-destructively. And one based on non-resonant interaction was also already mentioned by Rosario earlier in the morning from the book of Susanne Delving. They essentially suggested the 2D type setup where you have the molecule leading to an energy shift in the Rydberg atom, and then you need a conditional readout to detect that energy shift. It's in principle a nice idea, given the complexity of the molecular structure, maybe not quite as straightforward to implement. So the other idea is what I mentioned in my introductory slide, is Förster Resonance Energy Transfer, which was called in 1975 in a theory paper, where you have a cloud of atoms and a beam of molecules passing by, and when you look at atom and the molecule get close enough to each other, they flip their states, and then you detect the population of the Rydbergs in the end. So the molecule changes its state, but it doesn't get this. Okay, and so this was a theory proposal. There had already been experiments, notably the first one here in Seattle, Steve and also Martina in the audience. This is a figure from the title page of our booklet. And you recognize it where you see these whenever resonance is given. Then Martin and Tabitha also realized this from the data, but the radium Rydberg atoms And both is probably knowledge. So now, when we saw this, we said, well, the detection is already nice, but can you take this further? Can you make this state select? Can you really take this all the way to do some sort of molecular spectroscopy? Using not light, but the Rydberg energy. This is what you're saying, and it's a non-destructive spectroscopy of the molecule unlike ionization. How would you go about? Well, the idea is to get a resonance whenever a Rydberg transition frequency matches a molecular transition. And these Rydberg transition frequencies are tuned very easily with a starch shift and an external electron field. So the idea for the spectroscopy is quite simple. You prepare the Rydberg state as a function of the electric field strength. Then you let the polar molecule pass by this Rydberg atom, and you measure whether the state of the Rydberg atom is changed or not. And you vary the electric field strength and measure the cross sections such as this. Okay, so whenever you have a peak, you get the resonance, and indeed, and what is the key here is that the molecule essentially stays at the same energy, which is really cool, because the molecular starting point is so much smaller than the starting point of the atom, and then the atom, it always stays, they show this electrical dependence and allow you to differentiate between these. So here's a more in-depth picture of what is going on at the level of theory. So here's an example of Rydberg state where we have these projection quantum numbers, and for the Rydberg atom, we can actually compare those things very easily. And in the molecule, the equivalent is the orientational quantum number, uppercase there. The molecular rotation, these you cannot repeat. This is just part of the molecular rotation, so we will have to have it. And then the interaction is, in terms of very basic physics, that of the charge distribution of the Rydberg electron with molecular vacuum. And you'll see that the lowest order, we can very well approximate this by vacuum vacuum. And this is a picture that Rosario already showed. Here's what we did, is that the motion, the relative motion is still comparatively fast. So we're not interested in making molecules, but we just let them pass by. And then this motion we can treat classically. So the distance between atom and molecule, that is a time-dependent function, and this in turn makes our interactions time-dependent. So for the theoreticians in the audience, it's our setup. We can do this classical approximation of the relative motion because the kinetic energy is significantly larger than the interaction, and this is okay all the way down to velocity of about 0.1 meters per second. And then we approximate the interaction by the familiar vacuum term, and you see that we have here this difference, and then makes our interaction independent. We use just classical mechanics, again, textbook, to calculate this trajectory. We assume, that's another important assumption, that per atom we have one interaction. And if interaction doesn't change the molecular trajectory, which again is because of the time and energy scale. And then for a given value of the impact harmonic and the detunement between the atomic and molecular transition, we can calculate the probability for the atom to change its state as the molecule passes by. And then we don't control the impact parameters, so we have to average over all impact parameters. And this then gives us the cross sections, which I can this one. So now the line width that you see for those peaks depends only on velocity. Here was 10 meters per second. If you go down to 1 meter per second, you get line width below 1 megahertz, which is quite narrow. If you go to larger velocities, at some point you start broadening. And if you're at 100 meters per second or above, you will not really be able any longer to distinguish different transitions. Okay, but then maybe you have noticed here, for example, here, that we have different line shapes. And one may wonder why that is the case. And to this end, we approximated the internal structure by just two levels for the Rydberg atom and also for the molecule. Then we have a single matrix element that is relevant, and three types of transitions which are allowed in terms of selection rules. So, and my students make them crisscross, the Rydberg atom goes diagonally up, the molecule diagonally down, or flip-flop, either diagonal or linear. And now we can look at the time dependence of the matrix element that couples the states, and we see that in case of the flip-flop transition, we have a zero crossing of the interaction, whereas in case of the crisscross transition, the interaction energy stays negative all the time. And as a result, the dynamic state that is picked up because of this interaction goes to zero for the flip-flop transition, whereas it makes a jump for the crisscross transition. And this explains the various line shapes that we see. So because of the zero accumulated phase for flip-flop, we have this dip if you're right and reverse for those transitions, and we get the peak for the crisscross transition, and correspondingly compensate change or return to the original. And this is now a very simplified picture that allowed us to identify the connect the time dependent of the matrix element with what is seen in the cross section. But you see, if you look again at the cross sections that include the full state framework and calculations, that it matches actually quite well. It's just that the dips here don't go all the way to zero, which is in case of this. So with this, we can actually even assign which of the M states is involved. So let's say, states are not just the molecular energy. Okay, but so far what I have been hiding a little bit under the rug is that all these calculations are for a single molecular rotational level. And if you think of an experiment, like you speak to Stephen or Martin, then of course that would be very, very hard to actually achieve. But typically you have an ensemble, for example, a thermals. What do you do then? Well, here's the theoretical prediction that you get if you look at each of the rotational levels separately. The thermal ensemble just means we need to average over those. So this would be the signal that you would predict if you had a rotational temperature of 50 Kelvin. And you see that you can still very well assign the different transitions that with the solid lines have RK equals J, and with the dashed lines equals so when the equals in the audience. But you can still very well assign these peaks in the ensemble to the second rotational transitions. And then even infer the rotational population that we had in your initial. It doesn't have to be zero, we just put this. You can do this at 50K in this assignment, but it works even at 300K, so the spectrum becomes broader, the peaks become lower, but the inferring this ensemble population from the signal can still be possible for 2012. I see. And now, you have the freedom again to choose the ML quantum number of your Rydberg atoms. It can be 0, 1, and the peaks of course differ, and then you get more data. And another question that you may ask is, well, the rotational population is one thing, but what about noise in the experiment? How much noise can we deal with? And we added here some amplitude noise in this distribution. And you see that even by adding noise to the peak heights, this inferring the initial distribution is still possible to manage. So far, so good. Another concern that you may have is how good is this dipole level approximation actually that I made at the very beginning? That we can do it. And also this we can check because we can do a multiple expansion of the Rydberg average charge distribution. Here's just the usual Taylor expansion, and it's Taylor because we still are in a regime where the distance between the atom and the molecule is much larger when we look at radius. And this was the lowest order contribution that we looked at so far. Now you add and settle expression from electrodynamics that will protocol, that will often go even one further. It's not so nice to work all these various elements in terms of selection rules. It becomes easier, but it becomes still. And then repeat the calculation. So just to give us some more pictorial representation, why this may become an issue. It actually happens that often you have a dipole transition, which is energetically not too far from a probable optical transitions, like the given here. So, and this is, for example, the case of the video with N is equal to 45 degrees. Okay, so let's first assume that you don't have the dipole transition. So can we just use the quadrupole optical transition for the same type of spectroscopy? And the answer is yes, we can. It looks a bit more complicated. Because you have now, because of the larger state space for the Rydberg atom, more resonance that you can look at and more peaks. And so the velocities that you need to really resolve those peaks is a little bit smaller than in the case of the dipole transition, but still the same order of magnitude. And so in and you see that you really can resolve all these different level velocities. So, as I said, the peaks are resolvable not at 100 meters per second, maybe but 40 or something like this. And also in terms of cross sections, how much data would you actually be able to measure? It reduced only by 1 order of magnitude. Might expect a larger reduction because of the smaller measures. You could probe different types of selection rules. Selection rules again information rules because there's no line, it's always a little bit echo. So that's the spectroscopy. And the other question we ask ourselves is, well, what about this situation that we really have dipole transitions and quadrupole transitions being energetically very close to each other? Here's again an example from video and ammonia. And you see that the solid lines are dipole direction only. The dashed lines include the three terms up to octopole. You see that there's fairly similar, except that high field strength, when we start to get significant mixing of different L states. And there are two competing effects actually that determine whether you get here something which is zero or non-zero, like zero in the case of the Rydberg atom in the M equals 0 state and 1 for the Rydberg atom in the M equals 1 state. And these two competing effects are the start mixing that suddenly make transitions allowed before they're not allowed. And at the same time, because of the large field strength, the start shift starts increasing the detuning, the mismatch in transition energy, and that of course can prevent transitions. There is a balance between these two effects, whether you see or don't see something. In any case, at these large field strength, the cross section depends on the set of the Rydberg atoms or something that you could tune in an experiment. Okay, and then the final question that I was interested in is which term actually dominates the interaction? And the answer is for almost all velocities, it's the dipole term, which is marked here in yellow. And only at the highest velocity that we considered, what 500 to 600 meters per second, the quadrupole term starts to be stronger than the one. If you want to look for those terms in dipole position for enough, then it's kind of hard. So that we like this, except the medium one. For this, I'm already at the end of the talk. Let me summarize that part on the Rydberg spectroscopy. It's based essentially on resonant electrostatic interaction. What we suggest is to use the electric field to control the cross section, and then look at the relative population of rotational states, and we believe that this should be very straightforward for all velocities up to about 100 meters per second. If you want to get really narrow line efficient or smaller velocities, and the biggest advantage of this method compared to other molecular spectroscopies like microwave or established tools is that it works at very, very low molecular density. You just need to make sure that your molecules seem to be and the results which I presented were for for ammonia, for the inversion mode of ammonia, but it actually applies to a wide host of rotational transitions because you just need to find those kind of conditions that are in the areas. You can do this across the gigahertz and the terahertz range. Maybe we can do in particular low molecular density for the happen to work with hormones. Let me highlight this has all been the work of the CATMIN students that we have touched, who read in collaboration with Martin Sevenberg for the spectroscopy work. I want to acknowledge the Periscope for the Rydberg circular state preparation in our hundreds and the nuclear attention.
Thanks very much, Christiane. So, do we have any questions? Yes.
So coming to the optimal control. You showed this protocol where you can prepare desired circular states, but it seems also that your solution is not unique, right? Because you said that crystals can be averaged out, and that's all can be anything. So what strategies do you have to find, let's say, unique solutions, or is there some way to constrain the problem more to find a globally unique optimal?
Well, there's no unique solution. Usually it depends on the resources that you put, and resources you can control with time or power. So if you start to reduce those, then you start to reduce the number of solutions. We didn't go to the minimum time, mainly for reasons that experimentalists could explain better than me. And then you can do various things, so either automatically try to find smooth solutions by including this already in your optimization functional, or you can do kind of post-processing of the path, which in our case is much simpler way.
But the last part, so where you have this higher speed collisions and the protocol becomes more for current intuition about why this is, I can't. Why should the protocol dominate the high speed?
It's a simple estimate. So the point is that the speed determines, I think, also the minimal the impact parameter, which is the most important one, so the minimal distance it dominates. And if this is larger, then at some point the higher order transitions take over.
Going back to the circular states, you mentioned the Paris group that was very impressive, but in the context of common gates, there's not there. From your understanding, you think it could be possible to be highlighted?
So from a theoretical point of view, there's not really a limit because they're not limited by decoherence on those dimensions. And in the first experiment, the 2% or a bit more that they had was within the detection. At some point, if you put this in the 5%, then of course the positive portion becomes an issue. But if you tell me what is your response function of your electronics, and you do this in my calculation, and I'll give you a positive person to find that is function. It's just that this of course is a lot of work because to work out the silicon function requires a lot of political work, but it can be included. So I would say in terms of as long as you're limited by computing powers, it's really huge opportunity that we're not control.
So I think Frederick was next, but like, you okay with me? Maybe you want to interject on this point, or
So what about coherence?
Of course, we can include the coherence and we do it, for example, when we do confirmation for superconducting that I mentioned earlier. And I have a whole different talk on control of open quantum systems. To my experience, you find more or less boring solutions because either what control tries to do is beat the coherence by operating fast, or you identify a decoherence from substrates, which is what happened in the work of ISC therapy. We don't have to know the decoherence from substrates, you can use control to define it for you. Okay. Or you get the kind of fast sequence that is similar to dynamical decoupling. But so far, if you have generic T1, T2 decay or dephasing, I didn't come across a control strategy that I hadn't known before. Now, if you go to structured environments, non-conforming effects, then the whole game differs, but then it becomes very non-universal, very specific. That's a short answer to something like this.
An intriguing property of the dipole quadrupole interaction is that the dipole's transition changes the parity, and the quadrupole, the other part, doesn't change the parity. So overall, the parity seems to be not completely maintained by the process. Did you look in your calculation where the parity goes?
We haven't looked, but I don't think in this case there is a concern because there's no problem.
No, but it's a dipole transition in the Rydberg, the dipole changes the parity, and the quadrupole transition in the molecule.
No, it's the other way around.
Oh, yeah, it doesn't matter, one or the other.
So it's a dipole transition in the molecule because always a molecular dipole, and it's a quadrupole transition.
Yeah, but the argument works
Yeah.
both way around.
But would you expect something interesting there?
I mean, I like nature to maintain parity.
But I can change parity with optical transition. No, I don't like a lot of nice state and.
Yeah, because you both don't get the parity. But in a collision, you have a system which consists at the beginning of what it is, and then you change the parity of one side, and you don't change the parity on the other one. So overall, you have changed the parity. So something additional must have happened. Perhaps you've excited the rotation of the two systems or something like that.
No, so the rotation is completely included. I think the point is, we probably want to have to go to formulate the dynamics of the electric charge. Because the main settlement, if you go back, why you get this, because of course the operator which is relevant here is still the operator for the Rydberg atom, and it says the same like we have for optical solutions. But probably you can think of this kind of exchanging the photon to exchange some photon for that is
We had, with Johannes, we had observed dipole quadrupole transition in Rydberg collision, and that I think leads us quite a bit.
yeah, I mean, there's also been work when making big credit to this on the obstacle. About 10 years ago, very optical at the particle transition and
Is the motion important there? I mean, to drive the quadrupole, because when they get faster, it's more likely. So it seems like this term that drives the higher order transition is coming from the motion.
The motion, we really separated the motion, right? The classical motion just becomes time independent. And I think the argument is what I second question is just the beginning distance of the motion, like they matter, which of the interactions would use.
I think we should finish there and thank Christiane again.